So good afternoon all. Welcome to the weekly session of our NPTEL PMRF Teaching Assistantship session, which is the Geotechnical Engineering 2 Foundation Engineering. Myself, Rituraj Singh Rawat, who is Prime Minister Research Fellow in Department of Earthquake Engineering from IIT Roorkee. This course is currently being tutored by Professor Dilip Kumar Bedia, who is Professor in Department of Civil Engineering from IIT Kharagpur. So, due to some technical constraints, we couldn't able to record this session on Tuesday, and I really apologize for that. So that's why the NPTEL team was also not able to upload the session. But uh, today I am recording this session so that you can watch uh, the recording of the solution of the sample question which I have prepared, so that this can be utilized for your future uh, purposes. So those who are joining the sessions for the first time, let me tell you, these are the interactive sessions which are meant to interact with our learners. We'll be discussing some of the important concepts which will be required to solve your sample questions. We'll be solving some of the sample questions. Along with that, we'll also solve some doubts. Apart from that, if you are having any other query, please feel free to post that in the comment section of this YouTube video. So let's start with our session today. So the first question which is there in front of you is you are having a rigid isolated footing which is resting on the sandy soil. The contact pressure at the edges and the center of the footing are respectively. So you are having a rigid isolated footing which is and the contact pressure you need to see at the edges and the center of the footing are respectively. There is zero, the maximum and the zero, the maximum and the minimum and the maximum. So let's see the solution for this. So the correct answer is the minimum and the maximum. So we can see this thing with this with the help of this diagram. So whenever you are having a flexible footing, so in the flexible footing, we assume that there will be deformation in the footing, but the undergoing pressure which the footing is subjected to will be the uniform throughout the footing length. So in both this case, your pressure will be uniform, and to counteract the deformation, we'll use a flexible footing. So in case of the cohesive soil, your footing deformation will be concave upwards, and in the case of the granular soil, your footing deformation will be concave downwards. While in the case of the rigid footing, the pressure which it is subjected to is not constant, and there will be a uniform uh, displacement in your footing. So here you can see the pressure which your footing is subjected to is not constant, and you can observe a uniform deformation in the footing. So yes, if in our case it is a case of a rigid isolated footing which is resting on the sandy soil. So the correct answer is the minimum and the maximum. Yeah. So it is a case of the sandy soil and you are having a rigid isolated footing. So it is a minimum in this case and it is a maximum at this. So yeah. So the correct answer is at the edges it will be the minimum, while at the center of the footing it will be the maximum. So the correct answer is D. And here comes the next question. You need to arrange the bearing capacity of the silo foundation in the descending order. So you are having the four cases with you, which is the ultimate bearing capacity, net ultimate bearing capacity, net safe bearing capacity, and the gross safe bearing capacity. So you need to arrange them in the ascending order. So please do that. We'll solve this thing within 2 minutes. So let's check the answer. It's ABDC, and let's see how it is. So usually your ultimate bearing capacity, if you see, is given by C and C plus Q and Q plus zero point 0.5 gamma B and gamma, right? Which where C is your cohesion and C and Q and gamma is your bearing capacity factor. Q is your overburden stress, gamma is your unit weight, and B is your width of the footing. So if you reduce the overburden pressure in this, you will get the bearing capacity, which you will obtain is the net ultimate bearing capacity, and then you are having the net safe ultimate bearing capacity, which is your QNS. If you divide your net ultimate bearing capacity by factor of safety, NS, it will be your QNU by factor of safety, right? And for the gross safe bearing capacity, QS equals to QNS plus gamma dA. Yes. So the correct answer here will be QU, and then you will be having the QNU, then you are having the QS, and then you are having the QNS. Why this is so? Because if you see ultimate bearing capacity is the maximum, then if you reduce the factor gamma dA, so this will be the second case, and since you are dividing this by the factor of safety, so this will be QNS, and this will be the QS. So QU, QNU, QS, and QNS. So that is the case. And if you see the ultimate bearing capacity of a soil is, so this is the question number third. Here you need to calculate the net safe bearing capacity. So the ultimate bearing capacity of the soil is given to you, which is 300 kilopascal. The depth of the foundation is 1 meter. The unit weight of the soil is 20 kilonewton per meter cube. The factor of safety is 2.5, and then you need to evaluate what is the net safe bearing capacity. So you can go with the same question, same solution which you have seen. So let's check with the safe pairing capacity. So the net safe pairing capacity formula is given here, which is हाय हाय ये लो थोड़ा स्वीट कम ही खाता कोई ना थैंक यू दो ले जा सकता हूँ ले जाओ तीन ले जाओ रूम में ले जाओ इतना इतनी बेइज्जती नहीं करनी होती सर क्या आप भी सही मुफ्ती से ले लो नहीं मतलब हाँ तो बता दो नहीं वाला तीन है क्या हुआ इसको बता दो नहीं तीन है मुझे एक ही है नहीं मैं चुप रहूंगा QNS QNS effect of safety. So QNS equals to QNU by factor of 50, and let's check this. So how to calculate the QNU? So it's none other than your QU minus gamma DF. So your QU is 300 minus gamma DF is 1, depth of the foundation is 1, gamma is 20 kilonewton per meter cube. So it's none other than 280 kilopascal, and now the safe bearing capacity is another 280 by factor of safety, which is 2.5. So which will come out as 112 kPa. So the correct answer is 112 kPa. Moving to question number 4, you are having a shallow foundation square which is shaped in place of a cohesion-less soil. For phi equals to 0 degree, the bearing of bearing capacity shape factor as gamma of the foundation is. So let's solve this. So here the bearing capacity shape factor is given by S gamma is 1 point minus zero point 0.4 B by L. 1 minus zero point 0.4 B is the square footing, so it's 1 by 1. So your 1 minus zero point 0.4 is none other than your 0.46. So your S gamma is equals to 0.6. So what's the correct answer? Oh, it's 1. Mm-hmm. Let me check this. Yeah, so let's collect the answer. The correct answer will be 0.6. Correct answer is 0.6. Yes. So S gamma is 0.62. For the strip footing, it will be 1, but since it's a square footing, so your answer will come out like this. Because the another formula which is there, S gamma is equals to 1 plus 0.1, 1 plus sine phi by 1 minus sine phi, B by L, right? So it's 1 plus 0.1, and this factor will be 1 and this will be 1. So either it will come out as a 1.1. So let me check the formula. What is the correct one in the lecture notes given by Dr. Dilip Ambedi. Correct answer will be 1.1. Let's check the next question. So you are having a scarp foundation which is 1.5 meter below the ground surface of the dense corrosion the soil. The unit weight of the soil is 21 kg per meter cube and its interfriction angle is 34 degrees. So phi is equals to 34 degree. Tarjagis bearing capacity factor and say NQ and gamma this. During the subsurface soil examination, no groundwater was found. The factor of safety is 0.0. What is the safe bearing capacity of the footing? So you need to evaluate the safe bearing capacity of the footing. So with this expression, if we see what is the self ultimate bearing capacity, so it's q and u minus gamma df. Q and u is equal to q minus gamma df. 's cohesionless soil, so this term will go to 0. So your q ultimate is none other than gamma df and q plus 0.4 gamma b and gamma 21 depth of the foundation. let's calculate the Q ultimate from this. So Q ultimate is none other than your 1852.7292 kPa. So if we see the factor of safety, 3.0. So if we calculate this, it's 618. If they are asking for the net ultimate, yeah, so we need to further less. So it's another than 618 kp. So the correct answer is 638.6. So there's a check we need to do. Let me check. flight change. So here we need to add the overburden stress also, because we here they're asking for the gross safe bearing capacity, not the ultimate bearing capacity. So adding the gamma df, so which is none other than 649 kPa. So the correct answer is B. Yeah, 638.6 kPa. Moving to next question. Since this is the closer, so that's why we are taking that thing into account. You are having P, which is 3700 kilonewton. The internal friction angle is 37 degree. Cohesion is 15 kPa. Gamma dash is 21 kilonewton per meter cube by NC and Q, and gamma is given to you, which is NC is 70.01 and Q is 53.80 and gamma is another than 65.27, right? Factor of safety value is 3.6. Then you need to calculate the size of the footing is. Yeah, please do this. Let's check the answer for this. 70.01, and then you are having gamma dfn2, which is gamma is 21, depth of the foundation is 1.8, and q is 53.80 plus 0.4, gamma is 21, b size of the footing we need to determine. Into n gamma is your 65.27. So if you solve this, the q value which you will get here is 3398.83 plus 548.27 into b. So if we solve this, this will come out as a q nu by factor of safety plus gamma df into b square is equals to 3700, right? So you are 97.1.42 plus 152.3 into p square is equals to 3700. So now you need to calculate the b is how much. So b will come out as 1.500. So b value is 1.500. Moving to question number 7. You are having a rectangular foundation that is 2.8 meters by 4 meters in plan, 1.5 meters below the ground surface. The footing is subjected to a vertical load with a saturated unit weight of the soil of 21 kN per meter cube. For phi is equals to 28 degree, Tarjagi's bearing capacity and N and gamma are given to you. The natural water table is at a depth of 5 meters below the ground surface. Sorry, so there's a correction in this answer also. I don't know who made this. So the correct answer is E, which is 1.500 meter by 1.500 meter. So this we need to cancel. Moving to question number 7 to 9. You are having a rectangular footing which is 2.8 meter by 4 meter incline, 1.5 meter below the ground surface. The footing is subject to vertical load with a saturated unit weight of 21 kg per meter cube. Phi is equal to 28 degree. Target bearing capacity is this respectively. The natural water table is a depth of 5 meters below the ground surface. Apply Muir's methods for bearing capacity calculation. let's solve this. So for the rectangular floating, the value of the depth factor DC we need to calculate. So C is your 12 kPa, gamma is equals to 21 kilonewton per meter cube, and Cn Q gamma is given to you. So for calculating QU, it's CNC SC DC IC plus gamma DF and Q SQ DQ IQ plus 0.5 the N gamma S gamma D gamma I gamma. So for calculating the depth factor 1 plus 0.2 D by B 10 45 plus 5 by 2 D by B. So DC will come out as the 1.17. Considering the other factors as well, which is the DQ and D gamma, 1 plus 0.1 1.089. Yeah, so the correct answer is 1.08. Yeah, for DQ D gamma is 1.1, but in the calculated answer DC, so it's yes, it's the 1.178. Moving to next question, you need to calculate the ultimate bearing capacity. So it's a rectangular foundation having the dimension 2.8 meter by 4 meter in plan and 1.5 meter below the ground surface. The footing is subjected to vertical load with the saturated weight of the soil 21 kg per meter cube for 5 plus 28 degrees. Target bearing capacity are given to you. The natural water table is at a depth of 5 meter below the ground surface. So DC, DQ, D gamma we have calculated. For the other factor, we need to calculate the depth, shape factor as well as the inclination factor. SC is equals to 1 plus 0.2 B by L 10 square 45 plus 5 by 2 1.388, and in other terms SQ is equals to S gamma 1 plus 0.1 B by L 10 square 45 plus 5 by 2 is equals to 1.19. So IC is equals to IQ Right. So these all are the factors SC, SQ, S gamma, IC, IQ, A gamma, right? So So there's no effect of water table which need to be taken into account because it's less than b. So for calculation of the q, so these all are the things we need to take into account. So the ultimate bearing capacity will turn out as 1621.3 kilonewton per meter square. Let's check the next question. Yeah, so this is the ultimate bearing capacity which we have calculated, is 160.3. Moving to the question number 9. The eccentricity comes into the picture. A 15 centimeter eccentric force is being applied to the footing in the direction of width. Then for the rectangular footing, the value of the shear factor is. So let's say you are having the 2.8 meter by 4 meter in plan. So let's check this. So you need to take into account of the eccentricity, and then you need to calculate the value of the shear factor. So let's check the answer for this. So now in the formula of the shape vector, b dash equals to b minus 2ex. So b is your 4 minus 2 into eccentricity of the ex, 15 centimeter, which is none other than 0.15. So 4 minus 2 into 0.15 is nothing but 0.3. So we need to consider the smaller dimension. So b in this case is 2.8. So minus 2 into 0.15, which is another than your 2.5. Your shape factor is then given by s is equals to 1 plus 0.1 b dash by l tan square 45 plus 5 by 2, and which is your 1 plus 0.1 2.5 by 4 is your 1.173. Correct answer is C, 1.17. Moving to question number 10. You are having a rectangular footing which is 4 meter in length, 3.5 meter. It is loaded at an eccentricity of, let's say, 0.3 meter, which is having a load of 4000 kilonewton. We need to find what is the minimum contact stress below the footing in kilonewton per meter square. So your rectangular footing, it's having a dimension of 3.554 meter. Your eccentricity is none other than 300 mm. Your P is equals to 4000 kilonewton. So your Q minimum is P by BL 1 minus 6E minimum, whereas your Q max P. So 4000, your B is 3.5 into 4, 1 minus 6 into 0.3 by 3.5, which will turn out as will be 138.78 kilonewton per meter square. So the correct answer is option A, 138.7. So you have rectangular footing which is subjected to an eccentric load of 0.3 meter from its middle case. So there will definitely will be Q minimum and Q maximum which will get generated. So your Q minimum will be given by P by BL 1 minus 6 by E minimum 1 B, and it will be 138.78. Now for the influence factor for the immediate settlement of the footing depends on its Footing depends on the size, shape, and rigidity. Let's check how it is. So usually whenever the consolidation happens, there are three cases of consolidation. First is your immediate, sorry, three cases of settlement. First is your immediate settlement, second is your consolidation settlement, and third is your secondary settlement, which is happens to the Greek. So usually your immediate settlement is given by QB 1 minus W square I into E, right? So B correspond to your shape, mu is your Poisson ratio, and I is your influence factor. So the correct answer is size, shape, and rigidity. Moving to question number 12. So Sherman indicated the greatest strain influence factor would occur at. So where your greatest influence factor will occur at as per the Sherman. Yeah, so let's check the answer for this. So usually if you see the case, the distribution of the stress as per the Sherman is given in this form. So your IQ max is given by zero point 0.5 plus zero point 0.1 QCF by sigma dash p, right? And this value QCF is your none other than your stress at that point minus gamma df. And this distribution of IF, if you check as per the Sherman is usually occur at a depth of df by 2. So depth equal to half the diameter of the footing. So yeah, greatest influence factor would occur at the depth equal to half the diameter of the footing. Moving to question number 30. So now you need to determine the reduction in the volume of the soil primarily due to the squeezing out water from the voids is known as. So we know like if there's a reduction in the soil volume due to the water reduction, it's known as the primary conservation. Moving to the last question for today. So the natural void ratio of the saturated clay strata is 3.5 thick is point the final void ratio of the same clay at the end of the consolidation is expected to be 0.516. The total consolidation settlement of the clay strata is. So we know delta H by H is none other than your delta E1 plus E naught. So if you check the reduction in the height, delta H you need to determine, right? And H into delta E1 plus E naught, right? Your H initially is 3.5 meter and your change in the void ratio 0.924. So it's 0.924 minus 0.516. So it's your 1 plus E naught, which is 1.924. So your delta H is 3.5, 0.924 minus 0.516, 1 plus 0.924, which is your, let's check this, 0.742 meter. So in centimeter, it's none other than 74.2 centimeter. So correct answer is this. So that's all for today. We'll see on next Tuesday. Means on the upcoming Tuesday. Those who are having any doubts, you can upload your questions, queries in the comment section of the YouTube video. We'll definitely address it. Thank you.